Before we can jump in and write clients and servers with sockets, we first need to have a look at DNS IP addresses and their respective data structures. Most applications only require DNS names as input from the user because that is the right thing to do. Unfortunately, many system calls we will look at will require IP addresses as parameters. So the first step is usually to make DNS requests to resolve a name to one or more IP addresses. That is what this video is about, the interface to the DNS. The only data we have come across so far is the socket, which is fairly underwhelming because it's just an integer, more precisely a file descriptor. This does not help us to address a host across the network. As a minimum, we need IP addresses and port numbers, and if a DNS name is the starting point, we need to convert it into an IP address using the DNS. Clearly, we need data structures for this and utility functions that help us to talk to the DNS. So our starting point from here on is a DNS name, something that we can use in order to get into contact with a communication peer. www.example.com would be an example of a DNS name. Let's have a look at how we transform that name into one or more IP addresses. The system call that implements all this magic is called getaddrinfo, and we will see that it plays an important role in creating address family agnostic code. When the call to getaddrinfo succeeds, then it returns 0, otherwise it returns an error code. Error handling here differs a bit from many other system calls, such as the socket system call that we have seen earlier. Many system calls set the error number, which you can convert into an error string with the p-error function or the string error function. Getaddrinfo, however, has its own error handling facility with a function called GAI string error, where GAI stands for getaddrinfo, which takes the error code as returned by getaddrinfo as a parameter and creates an error string from it, which is the function's return value. Getaddrinfo takes 4 parameters. The first one is called node, and what you typically would put here is a DNS name, or more precisely, a null-terminated string representing a DNS name. That could, for example, be www.example.com. Getaddrinfo will use the DNS to resolve that name into one or more IP addresses. If you already have an IP address string, you can also put that here. That means DNS will not be invoked, but the IP address string will be transformed into a representation that can be used by subsequent system calls. So whether a DNS name or an IP address string is your starting point, always go through getaddrinfo. The second parameter is called service. This parameter is also a string which either contains a service name such as HTTP or a number representing the port number of that service. For the curious, the service names can be found in the services file located in the etc directory. Now, port numbers are not relevant for the DNS resolution process, but they are important when actually connecting to a host. Getaddrinfo helps you to create structures that contain all the information you need to subsequently go ahead and start talking to a host over the network. So providing the port number is needed for this. You can call getaddrinfo without setting the service or without setting the node parameter, but at least one of the two needs to be provided. I urge you to always provide both, otherwise you will need to do that in a second step in your code later anyway. The third parameter is called hints, and it allows you to specify exactly which kind of socket you want to create from the data that getaddrinfo is providing you. Here you can specify, for example, which transport protocol you would like to use or which address family you are interested in, and getaddrinfo will use these hints to prepare the result of the function call. You can call getaddrinfo with this parameter set to null, but then again you will need to set things manually later on, and you might get more results than you actually need and need to iterate through them to see which ones you want to use and which ones you do not need. The result of getaddrinfo is the fourth parameter. It will contain a linked list to addrinfo structures, each containing an address that has been resolved with the restrictions that have been applied by hints. The caller does not need to worry about memory allocation, which will be done by getaddrinfo itself. Both the hints parameter and the results make use of the addrinfo structure. It is time to have a look inside. This right here are the members of the addrinfo structure. The upper 4 members are primarily important when the structure is used as the hints argument. That means for specifying what you want to be part of the results. The latter four are filled by getaddrinfo, and these members will subsequently be used mostly in further socket-related system calls. Let's first have a look at how the structure is used as a hints parameter to the getaddrinfo function call. The AI flags member controls the behavior of getaddrinfo. I'll only point out 4 examples here, but there are more. Using the flag AI numeric host, you can specify that the node contains a numeric host address rather than a DNS name. By doing this, you can skip DNS resolution and convert the provided address directly. AI numeric serve is the equivalent for the service parameter. When you use a string representing a port number instead of the service name, you want to use this flag. Once we start to write servers, the AI passive flag will come in handy, because the server is not contacting other clients, but is being contacted first. A supplied IP address should be one that is locally configured. Typically, a server accepts connection attempts at every locally configured IP, and AI passive will make sure that that is properly set up. But be sure then to not actually provide an IP address or DNS name. In other words, in this case, the node parameter of getaddrinfo needs to be null. Finally, DNS resolution might return both IPv4 and IPv6 addresses, but one or the other address family might not be configured on your host, which makes those addresses unusable. In order to only get addresses that are indeed usable locally, pass AI address config as a flag. Multiple flags can be combined by bitwise ORing them together. Not all combinations make sense, however. For more flags, at this point I will only refer to the main page of getaddrinfo. The second member of the address infrastructure is called AI family. You might have guessed from the name that the address family can be specified here. So for example, if you only want the IPv4 address returned by getaddrinfo, you could specify that here with setting AI family to AFINet. For IPv6, you could simply use AFINet6. But as already mentioned, these days we really should make sure that we use every address family that the host can work with. So typically you would specify AF_unspec, which stands for an unspecified address family, and should return every address family that is usable with the provided node and service. This is what you can use as the first parameter in the socket system call, which we've already seen in the previous video. The third parameter is called AI sock type. When used as a hints parameter, you can specify the transport protocol here that you intend to use, which most likely will be either sockdgram for UDP or sockstream for TCP. Leaving this unspecified will probably give you more results as you typically want, so do not forget to set this. Also, this parameter should be familiar to you by now, because it is the second parameter in the socket system call. This leaves the fourth and last parameter we can set when we use the address infrastructure as a hints parameter, which is AI protocol. And this should not come as a surprise now, but it really is the third parameter that you can pass to the socket system call. And that already concludes this quick rundown of the parameters list that you can set in the address infrastructure when it is used as a hints parameter. Make sure you always set this information and the flags appropriately. This will save you a lot of manual work later on in the process and will make sure you write address family agnostic code. Now it is time to look at the actual result of a call to getaddrinfo. As already mentioned, the return value is a linked list of information that we will need for subsequent calls around sockets. The first two of the remaining 4 members of the address infrastructure need to be looked at together because they actually do belong together. The AI address lang member specifies the size of what the following member points to. Since we deal with multiple address families of different sizes, we need to do a few things now that aren't all that elegant. But given that we know the size of things, we know what to do when. So let us look at what can be behind the pointer called AI address of type struct sockaddress. Struct sockaddress has 2 members. One is also holding the address family, because you might just be dealing with this structure without the surrounding address infrastructure, and when that is the case, you still need to know which address family you are dealing with. We will see that a lot of system calls will accept a sock address structure as a parameter, So these kinds of functions will need this information. The second member of the structure is basically a 14-byte placeholder. But you do not need to pay a lot of attention to this, because if you as a programmer need to deal with what's really inside this data, which is mostly an IP address and a port number, you will need to cast it to an address family specific structure. Let's first look at the IPv4 case. If the sock address structure is containing an IPv4 address, you can cast it to a sock address _in structure. The first member of that structure is still the address family, which is important in order for this casting to actually work. The address family is followed by a port number, which is the one you have specified in the service parameter of the getaddrinfo function call. So if you provide it there, you won't have to come here and set it yourself, which saves you casting to the right structure and descending all the way here. The port number is followed by the IPv4 address, which is followed by padding bytes. The address is another structure, as you can see at the very bottom, which solely holds an unsigned 32-bit integer, which is exactly the size of an IPv4 address. In case you deal with an IPv6 address, you cast to a different structure, which is called sockaddress _in6. Again, in order for the cast from a sock address structure to actually work, the first member represents the address family. The second represents the port again, but what follows next is an IPv6 specific piece of information, and that is the flow label. The flow label is a number that routers use to tell which packets belong to a flow of packets. That primarily is all packets that are part of the same TCP connection, because TCP reacts sensitive to packet reordering, and the network tries to treat these packets in a way that they do not arrive out of order at the other end. The flow label is followed by the IPv6 address itself, which again is a structure. Since 128-bit integers are not common on most platforms, the address is encoded as a 16-byte character array, which can hold 128 bits. The last parameter is interesting for linked local addresses and is left as a reading exercise at this point. This is the most cumbersome interface we have come across as of yet. It practically means whenever there's address or port information you need to deal with, you'll have to worry about the address family. That is not what we want. We really want to write code that has as little address family specific code in it as possible. So the code snippet here is by all means something that we want to avoid as much as possible. Otherwise, there will be these if-then-else constructs all over our program. Fortunately, there is a structure that can hold both IPv4 and IPv6 addresses. And that is sock address storage. Whenever we can, we should be using this structure instead of one of the address family specific ones. That means whenever we have a pointer to a sock address structure, we will be using sock address storage to cast to and from that pointer instead of using one of the address specific ones. Hopefully, this will become much clearer once we start using these in code. This only really leaves the member AI canon name, which will contain the canonical name of the DNS name that was provided as the node argument to the getaddrinfo system call. That basically means the name that we provided was an alias and the DNS returned a CNAME record. It resolved that to actually get an IP address, but we can get the real name if we are interested in this. In order to actually get the name, the AI canon name flag in the hints argument to the getaddrinfo function call needs to be set, however. This was a lot to digest and we are nearly done. The last member of the addrinfo structure is a pointer to another addrinfo structure. If that pointer is non-null, then that is the next element in our list. In case it is null, we reach the end of the list. So now really is the time to apply all this knowledge by writing some code that does DNS resolution. But there's one more thing you'll need to know before you can safely apply all this. And that is freeaddrinfo. As mentioned earlier, getaddrinfo will do all the memory allocations to store the information we just went through. That does not mean the allocated memory is also magically freed again. That is the caller's job. Once you do not need those structures anymore, you will need to call freeaddrinfo to release the occupied memory. It is very important though that after the call to freeaddrinfo, you do not use any of those structures anymore, or otherwise you will likely crash your program. not calling freeaddrinfo will lead to memory leaks. If you only call addrinfo once in your code, that's probably not an issue. But if you do, and if you have long-running programs, such as a server, you will eventually have an issue. So make it a habit to free the memory allocated by getaddrinfo. Getaddrinfo is your go-to function for DNS resolution, where you have a name and want to resolve the IP address. That is also your typical use of DNS. There is, however, also the inverse operation, which means going from an IP address back to a name. That process is called reverse DNS. The respective function to perform reverse DNS is called getnameinfo. Just like getaddrinfo, getnameinfo returns 0 on success and an error code when it fails. Also here, you can rely on GAI string error to produce an error string from the returned error code. Getnameinfo takes as a first and second parameter a socket address structure and the length of that structure. These two we already know from getaddrinfo, since these are members of the addrinfo structure. The host and host length parameters that follow hold a pointer to a character array and the length of that array. The name of the host will be written into that array. In order to be on the safe side regarding the length of that array, ni_maxHost is a defined size capable of holding any domain name. If the caller is also interested in the service name, another pointer and length pair can be supplied as the next parameters. The maximum size for a service name is specified as ni_maxserve. The last and final parameter is again a flags parameter. The probably two most important ones are given here. With ni numeric host, you can specify that instead of the DNS name for the supplied IP address, you really want a string representation of that IP address. Just as with getaddrinfo, DNS resolution is not performed in this case, but a simple conversion from a socket address structure to a printable IP address is performed. Ni numeric serve does the same for the service name. Before writing the next little program, let's introduce a new tool that you might want to make use of while developing your programs. You might be familiar with Wireshark, which is a program that lets you inspect the packets the applications on your host sends and receives. The graphical user interface is actually quite nice, and filtering and dissecting packets is easy. Use it if you can. Sometimes, however, you simply do not have a graphical environment or just want something quick and dirty on the command line. In those cases, tcpdump is the tool for the job. The synopsis of tcpdump is shown here. Basically, tcpdump takes a number of command line switches followed by an expression which filters the packets that tcpdump displays. Here are a few useful options such as -A to print packets in ASCII or -I to specify which interface to sniff packets from. For the filter syntax, please refer to the pcap filter man page. Getaddrinfo is a really important function, so make sure you get familiar with it, and the only way to do this is to write code and play with it. So write a small program that does a DNS lookup of a name that is entered as the program's sole command line argument. Go through the results and print the address family, the protocol, the canonical name, if it exists, and the IP address from the addrinfo structure. If you need inspiration, there is program code at the end of the getaddrinfo man page. Since we want to see what, if any, packets are sent out by a call to getaddrinfo, use tcpdump to sniff on your network interface. The filter expression you want to use is UDP port 53, which is the DNS server port. This exercise is intended for you to get familiar with the DNS lookup part of network programming and have a go at another useful tool, tcpdump. As homework, please play around with various hint parameters and in particular with the flags. See how the outcome of getaddrinfo changes depending on your choices. Happy coding!